Welcome to Next Gen Manufacturing. Have you ever really looked at a Formula One car and wondered how it can crash at 200 miles per hour, yet the driver just walks away? Or a wind turbine blade, longer than a football field, withstanding hurricane-force winds without a single visible bolt holding it together? The secret to all of it is an invisible force, and it's completely changing the way we build everything. I mean, we're used to building things with screws, nails, welds, the classics, right? But what happens when you're working with materials so advanced that those old-school methods just aren't an option anymore? Well, the solution is chemical, not mechanical. It's a technology that creates bonds that can be even stronger than the materials themselves, all without a single screw, rivet, or weld in sight. And today, we're going to show you exactly how it works. To really get a handle on this invisible technology, we need to rewind the clock a bit. It all starts with the problems, the limitations of the materials that built our world for centuries. Just take shipbuilding. For ages, it was all wood, but wood rots. Then came steel, which is incredibly strong, sure, but it's also super heavy and, it rusts. Industries needed something better, a real game changer, materials that were lightweight, incredibly strong, and completely corrosion-proof. And that's where composites like grass-reinforced polyester, or GRP, and carbon fiber come in. They completely changed the game, making it possible to design things that were lighter, faster, and way more durable. But these miracle materials, they came with a brand new challenge. How do you actually join them together? You can't weld them, and if you drill holes for bolts, you're literally creating weak spots in the material. So what's the move? So the original solution was something called stratification. The idea was pretty simple, really. Just build a joint out of the same stuff as the parts themselves, fiber and resin. You'd lay strips of fiberglass mat over the seam, soak them in polyester resin, and basically create this solid bridge between the two pieces. And for a long, long time, that was just how it was done. But standard doesn't always mean best, does it? Engineers started asking a really critical question. What if, instead of physically layering a joint, we could chemically fuse the pieces together? This question, well, it marked a huge shift in engineering. And that brings us to the ultimate stress test. To finally settle the debate, researchers at ITW Plexus decided to put the old and new methods to the test in a real head-to-head competition. So here's the setup. They took a standard composite boat hull and attached a structural stiffener. That's a piece that stops the hull from flexing. One stiffener was put on using that traditional polyester stratification method, while the other was attached with a modern, high-performance methacrylic adhesive. Then they just started applying pressure until something broke. First up, the traditional method. The stratified joint held strong, but it eventually failed under a force of 114 kilonewtons. Now, that's a respectable number. It's the kind of strength that built boats for decades. But now for the modern adhesive. The result was just staggering. The bonded joint held until the force hit 198 kilonewtons. That is a 73% increase in strength over the old method. The adhesive wasn't just joining the pieces, it was creating a fundamentally stronger system. But pure strength is only half the story. What about endurance? I mean, a boat hull is constantly being battered by waves. Millions of small impacts over its life. In fatigue tests designed to simulate this, the results are just as dramatic. While polyesters and even standard epoxies fail relatively quickly, the specialized methacrylic adhesive can withstand millions of these stress cycles without even flinching. So how can something more flexible actually be stronger? Think of it this way. The rigid polyester resin is like a pane of glass. It's stiff, but a sharp impact will shatter it. The high-performance adhesive is more like a sheet of tough rubber. It gives a little, absorbing and spreading the energy of an impact over a huge area. This flexibility is what allows it to endure so much more punishment before breaking. It's not about being rigid, it's about being tough. With such a clear victory, this technology just exploded beyond the marine world, and it started revolutionizing one industry after another. This is really the core of next-generation manufacturing. In construction, adhesives are used to create these sleek, lightweight building facades that are also amazing insulators. This technology is so robust, it's actually used to assemble entire bridges from composite sections, like the Aberfoyle Bridge in Scotland, and even to add new life to aging infrastructure by reinforcing concrete with these ultra-strong, bonded carbon fiber strips. And in high-performance sports, where every single gram counts, you'll find composite bonding absolutely everywhere. The carbon fiber safety cell of a Formula One car, the feather-light frame of a racing bicycle, the advanced internal structures of a high-performance windsurfer, they are all held together by these incredible adhesives. And this technology enables a really key engineering concept: sandwich construction. You bond two thin, strong outer skins to a thick, lightweight core, and what you get is a panel that's both incredibly light and incredibly rigid. This is the secret behind everything from airplane interiors to those massive wind turbine blades we talked about. So, what does this all mean? What's the big takeaway? We're witnessing a fundamental shift in how we build our world. The old ways of drilling holes and just forcing things together are being replaced by a much more elegant, chemical approach. By moving from mechanical fasteners to chemical bonds, we can create things that are just better. They're lighter because you eliminate heavy bolts and overlapping materials. They're stronger because stress gets spread evenly across a whole surface, not concentrated at a few weak points. And they're way more durable, able to absorb shocks and vibrations that would destroy a rigid joint. And that leaves us with a fascinating thought. For all of human history, strength meant bolts, welds, and rivets. Now, it means molecules. So if the strongest things we build are no longer held together by mechanical fasteners, but by chemistry, what new designs, new efficiencies, and new possibilities will that unlock tomorrow? Thanks for joining us on Next Gen Manufacturing.